Hello everyone, welcome to Basic Electronics Tutorials. In this video, I'm going to discuss on the BJT configurations. Please note, I have already discussed about the construction of a BJT in my previous video. That video is a prerequisite for this video, so I would highly recommend you to watch that video first. You can watch it by clicking on the link shown in the top right corner right now, or I'll leave the link of the same in the video description below. Let us now start about the discussion on the BJT configurations. We know that a BJT is a three-terminal device and the terminals are named emitter, base and collector. Since a BJT has three terminals, there are basically three possible ways to connect the BJT within any electronic circuit by taking one terminal as common to both the input and the output. Such a connection is called a BJT configuration. It should be noted that each configuration responds differently to the applied input signal within a circuit. This is because the static characteristics of the BJT vary with the change in the configuration technique within a circuit arrangement. So, it becomes quite essential for any electronic student to understand the different BJT configurations and their behavior in the presence of voltages. The BJT can be connected to any electronic circuit under three configurations. The first one is called the common base configuration. Then we have the common collector configuration, and lastly we have common emitter configuration. Each of these configurations have different characteristics. Particularly, the common base configuration has a high voltage gain but no current gain. The common collector configuration has a high current gain but no voltage gain. And lastly, the common emitter configuration has both current as well as voltage gains. Let us now discuss each of these configuration techniques in brief detail. I am going to start the discussion with the common base configuration, and the equivalent circuit for an NPN transistor in common base configuration is shown in figure 1 here. As its name suggests, in the common base or grounded base configuration, the base terminal is common to both the input and the output. Please note the supply voltage VEE shown here is the input and the VCC shown on the other end is the output. So, we can say that the input signal is applied between the transistor's emitter and base. This is the emitter terminal and this is the base terminal. So, the input signal is given between emitter and base. And the output signal is taken from between the collector and the base. This is the collector terminal and once again we have the base terminal here. The base terminal, as already said, can either be grounded or it can be connected to some fixed reference voltage point. In my previous video, when I was discussing the construction and introduction to BJT, I have discussed the BJT has three currents and the currents are related in a fashion given by the equation. The emitter current IE is equal to the base current IB plus the collector current IC. In the common base configuration, the input current is the emitter current because that is where we have given the input signal, and the output current is the collector current because that is where we take the output from. If you look at the equation written here, which is IE equal to IB plus IC, you will understand that the emitter current is greater than the collector current. That is, IE is greater than IC. Therefore, in common base configuration technique, the output current IC is less than the input current. Because of this, we can now say that the common base configuration does not have a current gain and the current gain is less than or equal to 1. The notation for current gain here is alpha and this is equal to the output current IC divided by the input current IE. Since the collector current is less than the emitter current, the value of alpha is always less than or equal to 1. Due to this particular characteristic, we say the common base configuration attenuates the input signal. Further, you should also note that the common base configuration is a non-inverting voltage amplifier circuit. That is, the input signal V in and the output signal V out are in phase with each other. Also, this type of bipolar transistor configuration has a very high ratio of the output to input resistance. That is, the value of the output resistance RC is considerably greater than the input resistance RE. Because of this, we say that the common base configuration has high resistance gain. Right. We just learned that the common base configuration does not have current gain. What about the voltage gain? To understand that, let us denote the output voltage as V out and the input voltage as V in. The ratio of V out to V in is the voltage gain. Generally, it is represented by A subscript V, and as I said, this is equal to V out divided by V in. Let us now try to understand whether this configuration produces a voltage gain or not. As I said, the voltage gain is represented by AV and it is equal to V out divided by V in. I can write the output voltage in terms of its current and resistance, which is IC multiplied by RC. Please note, RC is also considered as the load resistance. In a similar fashion, I can also write the equation for V in as the input current IE multiplied by the input resistance RE. Let me now split this as IC divided by IE multiplied by RC divided by RE. It must be noted that the value of RC is considerably high as compared to that of the value of RE, and therefore, the value of RC divided by RE will be very high. Because of this, we say this configuration creates high resistance gain. Also, we have noted that the value of IC divided by IE is nothing but the current gain alpha, and although the value of alpha is less than or equal to 1, because of the ratio RC divided by RE, which is very high, the overall voltage gain will be considerably larger than 1. So, we can now say that the common base configuration has a very high voltage gain. It is because of this very high voltage gain characteristic of the common base configuration that we do not commonly use it in practical applications. It has very few applications, specifically in single stage amplifier circuits such as a microphone preamplifier or a radio frequency amplifier, because this particular configuration has a very good high frequency response. Let us now summarize the common base configuration. It is called as the common base or grounded base configuration, where the base terminal is taken as common and the input and output are applied to the other two terminals. Input signal is applied between emitter and base terminals, and output signal is taken between collector and the base terminals. So, you can see that base is common both for the input as well as output signaling. The base terminal is commonly connected to the ground, or it can also be connected to some fixed reference voltage point. In this configuration, the input current is greater than the output current, and therefore, the current gain is always less than or equal to 1. The current gain is denoted by alpha, and it is simply the ratio of the collector current to the emitter current, that is output current divided by input current. As I said, input current is greater than output current, so the value of alpha is always less than or equal to 1. Because of this particular characteristic, we now say the common base configuration attenuates the input signal. Also, this particular configuration is a non-inverting voltage amplifier circuit. That is, the input and output voltages are in phase with each other. Since the value of the output resistance, which is RC, greater than the input resistance, which is RE, we say this type of configuration has a high resistance gain. And lastly, talking about the voltage gain, we find that the common base configuration has a very high voltage gain. It is because of this unusually high voltage gain characteristic that the common base is not used in most of the practical applications. Let us now move on to the next configuration, which is common emitter configuration, and the NPN equivalent circuit for the same is shown in figure 2 here. In this type of configuration, the emitter terminal is taken as common to both the input and output. The input signal is applied between the base and emitter terminals. This is the base terminal, this is the emitter terminal, and the output is taken from between the collector and emitter terminals. This is the collector, once again this is the emitter. Let us once again rewrite the equation for currents in the BJT, which is IE emitter current equal to IB base current plus IC, which is collector current. As you can see in this configuration, the input current is the base current and the output current is the collector current. Before continuing further, let us analyze the values of the voltages applied across the input and output. In a very common practice, the value of VCC is always considerably high than that of the value of VBB. This directly implies that the value of IB will be low as compared to the value of IC. So, we now understand that in a common emitter configuration, the input current, which is the base current, is lesser than the output current, which is the collector current. Because of this, we can now say that the common emitter configuration has a high current gain, and the current gain parameter is represented by beta and is given by IC divided by IB, and it is greater than 1. It must be noted that the typical values of beta range between 20 and 200. So, how do we analyze this value of beta? If the transistor has a beta value, let us say 100, then this means that 1 electron will flow from the base terminal for every 100 electrons flowing between the emitter and collector terminals. So, we have now found that the common base configuration as well as common emitter configuration both have a current gain parameter. The common base configuration current gain is less than 1, whereas the common emitter configuration current gain is greater than 1. So, we need to now understand, is there any relation between these parameters? Yes, there exists a relation between alpha and beta. Let us look at that now. We know that the value of alpha, which is the current gain for common base configuration, is given by the equation IC divided by IE. And the current gain for common emitter is given by beta and is equal to IC divided by IB. If I rewrite the current gain equation for the common emitter configuration for IC, then I will get it as beta IB. In a very similar fashion, if I rewrite the equation for current gain of common base configuration, then I would get it as IC equal to alpha IE. So, you see that IC is beta IB, I will call it as equation 1, and IC equal to alpha IE, I will call it as equation 2. If I equate these two equations, what I would get? I will get beta IB is equal to alpha IE. If I simplify this equation, I will obtain the relation between alpha and beta as alpha equal to beta divided by 1 plus beta and beta equal to alpha divided by 1 minus alpha. Right. We have now understood that the common emitter configuration has a current gain. So, what about the voltage gain? So, the voltage gain represented by AV is simply the ratio of the output voltage divided by the input voltage. Output voltage is given as IC multiplied by RL divided by IB, which is the input current, multiplied by RIN. I can split this as IC divided by IB multiplied by RL divided by RIN. For the common emitter configuration, the value of the load resistance will be low as compared to that of the input resistance. So, if I substitute that concept here, the ratio RL divided by Rin will be less than or equal to 1. However, it is the other ratio, which is IC divided by IB, which is considerably high. As I said, it ranges between 20 to 200. Therefore, the overall voltage gain that is produced by the common emitter configuration is always greater than 1. Please note, we have now learned that the common emitter configuration has both current as well as voltage gains. You must note that the common emitter configuration has a very high input impedance. It has both current and voltage gains as well as power gain. However, if you compare the values of voltage gains for common emitter and common base, the common emitter configuration's voltage gain is lesser compared to that of common base configuration. Another important aspect about the common emitter configuration is that it is a inverting amplifier circuit. This means that the resulting output voltage has a 180-degree phase shift with respect to the input voltage signal. Let us now very quickly summarize the common emitter configuration. In this configuration, emitter is common to both the input and output. The input signal is applied between the base and emitter terminals, and the output signal is taken from between collector and emitter terminals. In common emitter configuration, the output current is greater than the input current. Therefore, this configuration creates a high current gain, which ranges typically between 20 to 200. The equation for the current gain is given by beta equal to IC divided by IB, and it is greater than 1. I have also shown the relation between alpha and beta here. Alpha is equal to beta divided by 1 plus beta, and beta is equal to alpha divided by 1 minus alpha. Coming to the voltage gain parameter, it is given by AV equal to V out by V in. V out can be written as output current multiplied by output resistance, which is IC into RL. V in is the input current multiplied by input resistance, which is IB into Rin. You must note that the common emitter configuration has a very high input impedance. So, the ratio of RL divided by Rin will always be less than or equal to 1. However, it is the other ratio, which is IC divided by IB, which will be considerably greater than 1. Because of this, the overall voltage gain of the common emitter configuration is greater than 1. And lastly, you have to note that this type of configuration is a inverting amplifier circuit. That is, the output voltage has a 180-degree phase shift with respect to the input voltage. Let us now move on to the last configuration, which is the common collector configuration. The NPN equivalent circuit for the same is shown in figure 3 here. In the common collector or grounded collector configuration, the collector terminal is common to both the input and the output. The input signal is connected directly to the base terminal, and the output signal is taken across the emitter and collector terminals. You should note that this particular circuit, what I have shown in figure 3 here, is not the commonly used circuit. I have another circuit which is an alternate circuit for common collector configuration, where instead of connecting the load resistance to the collector terminal, we connect it across the emitter terminal. Also, you should note the output is taken across the resistor, which is the load resistor, connected across the emitter terminal itself. Since the load resistance is connected across the emitter and the output voltage is measured across the same load resistance, this particular technique will have an output voltage equal to the input voltage. If you ask why, it is pretty simple. Look at the way in which the VBB is connected. It is connected across the base terminal and the emitter terminal. Where is the output measured? Across the resistance connected to the emitter terminal. So, the voltage V out is simply equal to V in. Because of this characteristic of this configuration, we call this circuit as a voltage follower or an emitter follower circuit. The common collector configuration is commonly used in impedance matching applications because of its very high input impedance and low output impedance. In simple words, the value of Rin is very high and that of the output, which is RL, is low. This particular characteristics makes this configuration most suitable for impedance matching applications. Let us now talk about the current and voltage gains for this circuit. Please note that the input current is nothing but the base current and the output current is the emitter current. Let us once again write the equation for the currents in the BJT. That is, the emitter current equal to base current IB plus the collector current IC. For the common collector configuration, you should note the current gain AI is the ratio of the output current IE divided by the input current, which is IB. Let us substitute IE equal to IB plus IC into the equation for AI. So, this will be equal to IB plus IC divided by IB. So, this will become 1 plus IC divided by IB. So, the final expression for the current gain AI is equal to 1 plus. Please note the ratio of collector current to base current, as we previously discussed, is equal to beta, which is the common emitter current gain. So, we can now say that in the common collector configuration, the current gain is almost equal to beta, which is the common emitter current gain. If I talk about the voltage gain, which is AV, it is simply the ratio of V out divided by V in. Since the output is taken from the resistance connected to the emitter terminal, we will find that the value of AV is approximately equal to 1. So, we can say that the common collector configuration does not have a voltage gain. Continuing, this type of configuration is actually a non-inverting circuit, that is, the voltages V in and V out are in phase with each other. Let us now quickly summarize the points for the common collector configuration. In this configuration, the collector is grounded. The input signal is connected across the base and emitter terminal, and the output signal is taken across the emitter load resistor. Please note, it is across the emitter load resistor. Because of this particular characteristic, we call this configuration as a voltage follower or emitter follower circuit. Also, this particular configuration has a very high input impedance and very low output impedance. This characteristic makes this configuration useful in impedance matching applications. The current gain of the common collector configuration is actually 1 plus beta, but since the value of beta is considerably larger than 1, we can say the current gain is approximately equal to beta itself. Please note, beta is the common emitter configuration current gain. The common collector configuration circuit is a non-inverting amplifier circuit where the input and output voltages are in phase with each other. The voltage gain of the common collector configuration is equal to 1. Therefore, this particular configuration is also referred to as a voltage buffer. And lastly, as already discussed, this configuration has a very high current gain. Right, that is about the discussion on the three configurations for a BJT. Let us now summarize the points discussed in this discussion by comparing each of the configurations. Consider the table shown here. In the leftmost column, I have listed out the characteristics. Then we have the common base, common emitter and common collector configurations listed in the next three columns. Let me start with the first characteristic, which is the input impedance. The common base configuration has low input impedance, common emitter has medium input impedance and common collector has high input impedance. Coming to the output impedance, it is exactly the reverse. The common base has very high output impedance, common emitter has high input impedance and lastly common collector has low input impedance. Coming to the next point, which is the phase shift between the input and output voltages. In the common base, they are in phase, therefore the phase shift is 0. In the common emitter, the phase shift is 180 degree, and lastly in common collector, it is once again 0 degrees. Coming to the next characteristic, which is voltage gain. The common base configuration has an unusually high voltage gain, common emitter has medium voltage gain, and common collector has low voltage gain. Talking about the current gain, common base has low current gain, it is less than or equal to 1. Common emitter has medium current gain, and lastly common collector has high current gain. Coming to the last characteristic, which is the power gain. The common base has low power gain, common emitter has very high power gain because it has both voltage as well as current gains, and the common collector has medium power gain. Right. With that, we have come to the end of this discussion on the BJT configurations. In my next video, I'll take up each of these configurations in complete detail and discuss their input, output as well as transfer characteristics. So, stay tuned. Well, that is the end of this video. If you found this video to be informative, kindly like and share this video and subscribe to my channel for more tutorials on basic electronics. Thank you for watching. Have a good day.